Hi everyone, welcome to another session of Mr. Techpathy Tutorials. This is part 4 of Linux device drivers. In this session, we'll discuss about Linux kernel modules, types of Linux kernel modules, which module type to choose while kernel programming, location of Linux kernel modules in a Linux PC or a device. Let's start with our first topic, Linux kernel modules. What exactly is a module in Linux? It's a piece of code that can be added to the base kernel. We'll be discussing about the base kernel in coming slides. If you are planning to add some code to the kernel, then it means that you are adding a module to the kernel. We can't just add code to Linux without any purpose. We add code to make a device like printer, Bluetooth, dongle, etc. to work. We call this piece of code as device drivers in Windows. Assuming many are familiar with Windows, we can draw one conclusion. As we have device drivers in Windows operating system, we have modules in Linux operating system. In short, device drivers are called modules in Linux operating system. Both terms can be used interchangeably. Before knowing about module types, we need to know about base kernel, user space, and kernel space. So, what is a base kernel? Kernel code which is compiled and loaded along with basic device drivers as a single entity is called base kernel. Note that all parts of base kernel will be loaded all the time. Once you have a working base kernel, it is good to leave it untouched as long as possible. Next, we'll discuss about user space and kernel space in Linux. From this diagram, base kernel along with kernel modules KM1 to KM10 fall under kernel space. Here KM1 and KM10 are just for examples. The name will differ in the real-time device drivers. User space applications fall under user space. So, what are user space and kernel space? Simplified answer is that the kernel runs in kernel space and normal programs runs in user space. Normal programs in user space can't mess with memory and other resources owned by other programs or by the Linux kernel. This limits their ability to corrupt things like crashing the machine. The kernel is the core of the operating system. It normally has full access to all memory and machine hardware. To keep the machine as stable as possible, you normally want the most trusted, well-tested code to run in the kernel mode or kernel space. Okay. Let's learn about the kernel modules now. There are two types of modules. One is static module, the other is the dynamic modules. What is a static module? Static modules are those which are compiled as a part of base kernel and is available at any time. From the diagram, you can see that the static modules are part of the kernel image. They are compiled and loaded as a part of the base kernel image. So, what is a dynamic module? Dynamic modules are compiled as modules separately and loaded as and when required. These are also called loadable kernel modules. In short, we call them as LKM from now on. Every kernel programmer should clearly understand about dynamic modules and how they work. From this diagram, we see that dynamic modules are compiled separately. They are not part of basic kernel image. To know how exactly dynamic module is loaded, we need to know 4 important steps. Step 1. From this diagram, assume that you have written a dynamic module XYZ. You will also write an application which tries to access the XYZ functionalities. This application sits in user space application and your driver sits in the kernel space. Step 2. Once Linux is up and running on your PC or an embedded device, you will dynamically insmode your XYZ module using an insmode command in Linux. You will be loading your XYZ module to the RAM during the runtime. We'll discuss about insmode in later sessions. Coming to step 3, your application in user space will try to access the functionality of your hardware through XYZ module by calling Linux provided system calls. Normally, they are called IOCTL calls. We'll discuss about IOCTL calls in later sessions. Coming to step 4, once the required hardware functionality is retrieved by the user application, when XYZ module is no more needed, we can request kernel to remove XYZ module using rmmode command. From this diagram, as you can see, the kernel issues the rmmode command which will remove your driver permanently from the RAM. Once after discussing about static and dynamic modules, we have a common question. Which one to use? Which is the best? Yes, always a device driver programmer has a choice between building his module as a static module or dynamic module. To decide on this, we need to first know few things. First, disadvantages of building your module as a static module. Second, the advantages of building your module as a dynamic module. First, let's learn about disadvantages of building your module as static module. Let's say you have written a module XYZ for a device driver. When you compile this as a static module along with your kernel, you will be adding extra size to the kernel image permanently. This is the first major disadvantage. As the kernel size grows, the time taken to load the kernel and size occupied by the kernel image in the memory increases. Whenever you modify your XYZ device driver, you need to recompile your entire kernel to build it. Also, machine need to be rebooted for the changes to take effect. One more important drawback is while your device driver is not stable, when you build it as a static module, you will be facing issues which takes more time to debug. Take a scenario where there is a memory overflow bug in your XYZ static module. Once it is statically compiled and the kernel is loaded, at some point of time the kernel may crash. In order to debug it, people may take hours or days to fix it. Also, your kernel, which includes this XYZ module as a part of it, will be useless till you fix the crash. This doesn't happen when you build your XYZ as a dynamic module. We'll see how in a short while. Coming to the advantages of building your module as dynamic module, let's say you built your XYZ module as dynamic module now. With this, you don't have to rebuild your kernel as often. It can be compiled separately. It saves you the time and spares you the possibility of introducing an error in rebuilding and reinstalling the base kernel. It can be loaded onto the kernel at runtime without having the machine to reboot. It saves you memory because you load them when you are actually using them. It can be unloaded anytime and hence no permanent effect on the kernel size. Since these are compiled and built separately from kernel, they are much faster to maintain and debug. Each dynamic module is made up of object code that can be dynamically linked to the running kernel by the ins mode program and can be unlinked by the rm mode program. Many have a misconception that dynamic modules are a bit slower than the static modules. I totally disagree with them because loading either one is simply a branch to the memory location where it resides. With information known till now, let's see the example which we discussed earlier about the overflow bug in your module. Assume this bug is present in your XYZ module which is built as a dynamic module. Once you boot up your Linux on your embedded device or PC, load your LKMs along with your XYZ dynamic module. After a while, when your system crashes because of overflow bug, to know if your XYZ module is causing the issue, you can just discard loading your XYZ module after next boot up and just load the base kernel along with your other dynamic modules and see if the system crashes. If the system doesn't crash, then it clearly shows that your XYZ module is the culprit and you can debug and fix the bug without any much headache. Remember, you can even use base kernel and other LKMs till you fix this overflow bug in your XYZ dynamic module. Hope everyone are clear with the explanation till now. If you are not clear, please drop me a comment or a mail. Okay, let's repeat our earlier question. As a kernel programmer, which one do you prefer, a static module or a dynamic module? The answer will be a dynamic module. As a good kernel programmer, one should prefer building their module as a dynamic module. So, when to use static modules? Of course, there are times where one have to build something into the base kernel instead of making it as a dynamic module. Anything that is necessary to get the system up far enough to load dynamic modules must obviously be built into the base kernel. For example, the driver for the disk drive that contains the root file system must be built into the base kernel. Coming to our final topic, where will be the location of the Linux kernel module in Linux device or a PC? To see the current module types, just copy and paste this command in your Linux terminal or a console. Use the following command to list all the drivers for various devices. You can just copy this command and paste it in that Linux terminal or a console. Here ends the brief explanation about Linux modules. Hope this session went very well and viewers are clear on all topics discussed. These days I have been receiving many mails from viewers asking to start module programming. Please note that I have been preparing these videos by keeping in mind about beginners in Linux device drivers. It will be really hard for the beginners to directly jump into the module programming before knowing the basic concepts of Linux device drivers. We'll surely start our Linux device drivers programming soon after learning basic concepts. That's all for this session. If you have any doubts, don't hesitate to drop a comment or a mail. Don't forget to subscribe Mr. Techpati videos. Thanks for watching. Goodbye for now.